Hey guys, welcome back to another video. In this video, we're going to learn about how if you change the standard conditions, that is 1 atmospheric pressure, the temperature and the concentration of ions, what is the effect going to be on the electrode potentials in each half cell. And we are also going to understand how to calculate the change in electrode potential granted there are changes in concentration of the ions. So previously, we're talking about electrochemical cells. I mentioned that your concentration of ions need to be exactly 1 mole per dm cube, right? So that would make it fall under standard conditions. Now, in this case, where you will be calculating electrode potential for non-standard conditions, your concentrations may vary. And to be able to calculate what your electrode potential will be in those cases, you need a formula that is called the Nernst equation, right? I don't know how to pronounce it, but I'm calling it Nernst equation. So starting off, we're going to learn about the theory side of it. That is, what is in theory going to happen based on the shift of equilibrium if we change the concentration of the ions. So that is the only change we're going to observe in this video, and that's pretty much the only change you need to understand in case of electrode potential, because the pressure and temperature is going to stay constant. However, the question may change the concentration. So that's the only thing we will focus on. Okay, now to mention the standard conditions again, the standard conditions are 298 Kelvin, 25 degrees Celsius, otherwise stated, and 1 mole per dm cube of ions, ion concentration, and 1 atmospheric pressure. Now, in case of the electrochemical cell, it can also take place under non-standard conditions. Now, what will happen in case that I change those concentration? So if we take an example of a half cell. So we take a half cell over here. This is going to be your metal ion half cell. So this is your platinum. This is connected to a voltmeter to another half cell, but we don't need that for this. So this is your 1 mole per dm cube of Fe2 plus and 1 mole per dm cube of Fe3 plus. This is your platinum wire. Okay, so you can see there is 1 mole per dm cube of iron 2 plus and iron 3 plus, right? Now, what's going to happen to the electrode potential? Now, in case of standard conditions, your electrode potential is positive 0.77. Now, what's going to happen if I change any of the concentration? Let's see what's going to happen theoretically. So I'll put this on the side. Okay. Now, if I change, that is, decrease the concentration of Fe2 plus, I'll denote with white. So if I decrease the concentration of iron 2 plus, that is your product, what's going to happen? Your product concentration has decreased. Therefore, your equilibrium shifts to the right-hand side, right? To produce more Fe2 plus, because your equilibrium will move to recover the same equilibrium constant, right? So to recover that equilibrium constant, it's going to produce more Fe2 plus or the more products. So equilibrium shifts to where? Right-hand side, right? Remember, your equation should be written in terms of reduction always. And this is why, because it makes it standard in terms of at least writing your answers in this case. So granted, you've written your equation in terms of reduction taking place. You know that if there's a decrease in iron 2 plus concentration, equilibrium shifts to the right-hand side, more Fe2 plus produced. However, in doing so, the concentration of electrons will also decrease. Why, you ask? Because the electrons will be used up to reduce Fe3 plus in producing iron 2 plus. Therefore, your concentration of electrons will indeed decrease. Now, how is it going to affect our electrode potential? So, since the concentration is going to decrease of the electron, your electrode potential will become more positive. So, think of it this way, that if the amount or the concentration of electrons decrease, that means the negative charge in the solution decreases, which is why your new electrode potential will increase. That is, turn into more positive, because you're decreasing the electron concentration, right? So what was the change that we did? We decreased the amount of product, or decreased the concentration of reduced species. You can also call this reduced species, because iron 3 plus has been reduced, right? And this is going to be your oxidized species. Right? Because if you oxidize Fe2 plus, this is what you get, Fe3 plus, right? Fair enough. So we saw if we decrease Fe2 plus concentration, equilibrium shifts to the right hand side, electron concentration decreases, electrode potential becomes more positive. And you can also say Fe3 plus is more easily reduced. Why? Because more electrons are used up, also more Fe3 plus will be used up to produce more Fe2 plus. So Fe3 plus is more easily reduced. More amount or more concentration of Fe3 plus will be reduced. Okay, fair enough. Now looking at the other changes. So I'm going to do this a bit fast because I've explained the most of it over here. So in case that you increase the concentration of Fe2 plus, that means you have enough of the product. Now, since there is an excess of Fe2 plus, more electrons in this case will be released to regain the equilibrium, right? So your equilibrium is going to shift to the left hand side, right? Equilibrium shifts to the left hand side to produce more electrons. So your electron concentration increases and your Fe3 plus concentration increases as well. More electrons available. Therefore, electrode potential will become more negative. Why more negative, you ask? Because the concentration of electrons have increased, right? Fair enough. So if concentration of electrons increase, that means concentration of iron 3 plus has also increased, because for Fe2 plus to release electrons, it had to turn into the oxidized species, that is Fe3 plus. Therefore, more electrons, that means more negative electrode potential. So let's say in this case, it would probably turn into something like 0.65 or even 0.72, right? So it becomes more negative, or decreases, you could say. So in this case, Fe3 plus is less easily reduced. Why is that the case? Because to regain the equilibrium, it shifted left hand side. Therefore, there is more of oxidization taking place. So the species are getting oxidized. Therefore, the backward reaction is taking place more prominently, which is why your concentration of Fe3 plus increases. Therefore, Fe3 plus, the forward reaction that is being reduced, is taking place in less amounts, right? At a lesser rate, right? Therefore, Fe3 plus is less easily reduced. So these two cases we have identified. Third case, what happens if I reduce the concentration of Fe3 plus? Let's see. What did I do? Okay, so if I reduce the concentration of Fe3 plus, reduce it, yeah. If I reduce the concentration of Fe3 plus, what's going to happen? There is lack of reactants in the left hand side. Therefore, the equilibrium will be shifted to the left hand side to compensate for the lack of reactants. Therefore, there will be less, the concentration of Fe2 plus will also decrease. Why? Because these species, that is the reduced species, have to again become oxidized to increase the concentration of Fe3 plus, because you have reduced the concentration of Fe3 plus. So to regain that equilibrium, Fe2 plus has to release electrons. It has to release electrons. Therefore, in this case, you will see more backward reaction taking place, right? So what do you see? More Fe3 plus and electrons released as equilibrium shifts to the left-hand side. Therefore, to compensate, more iron 3 plus ions will be released, right, to regain the equilibrium constant. Therefore, if that is happening, that means more electrons will also be released because your Fe2 plus is getting oxidized. Therefore, it's releasing an electron, right? So in that case, the concentration of electrons increase. And in doing so, what's going to happen? If your concentration of electron increase, more negative charge, therefore your electrode potential decreases. So decreases to an amount of, let's say, 0.72, right? More negative, or say it decreases. Either, right? Next, if your concentration of Fe3 plus increases, now they're telling you I'm increasing the concentration of Fe3 plus. So where will the equilibrium go? Where will the equilibrium shift towards? To regain the equilibrium constant, it will move to the right hand side in this case. Why? Because there is excess of reactants. So it needs to produce more products. Therefore, a larger amount of electrons will be used up. In doing so, greater amount of Fe2 plus will be produced. Therefore, more electrons used up, right? So it decreases. Concentration of electrons will decrease. Therefore, since concentration of electron decreases, therefore the amount of negative charge decreases. Therefore, your electrode potential will be more positive. So let's say to an amount of 0.79 or 0.81, right? So your electrode potential will increase or become more positive. Becomes more positive as number of electrons decreases. So if it is asked to you that the concentration of the oxidized species are increased or decreased, or the concentration of reduced species are increased or decreased, now you can answer in terms of where the equilibrium is going to shift, and you can now tell and predict whether or not the electrode potential will increase or decrease, right? So these questions may be of around 3 or 4 marks. So you need to talk about shift of equilibrium. You need to talk about the change in electrode potential, and you're going to talk about if the products are more produced or the reactants are more produced, or which side of the reaction is taking place, which rate is greater. Is it the forward rate of reaction greater or the backward rate of reaction greater? And to do what? To regain the equilibrium, right? Fair enough. So all those things, if you mention, you're going to get your mark. So, okay. So this is in theory what's going to happen. And now we're going to understand how to calculate the change in the electrode potential. So we saw the changes in concentration of the oxidized species or reduced species. Now we're going to see how we can take those into account and calculate the absolute change in electrode potential. Now to do that, we're going to use Nernst equation, and this helps us find the voltage under non-standard conditions. So even if the temperature was changed, even in that case, you would be able to calculate the change in electrode potential. However, they're going to keep the temperature constant. Yeah, they're going to keep the temperature constant, which is why you don't need to take that into account. So the formula for the Nernst equation states that the electrode potential, the new electrode potential, E, is going to be given by E naught, that is the electrode potential under standard conditions. That is, in our case, the reaction for Fe3 plus turning into Fe2 plus, it will have an electrode potential of 0.77 in standard conditions, right? So now in our case over here, you're going to add E naught, that is electrode potential under standard conditions, plus the the gas constant R times temperature divided by number of electrons times Faraday's constant, right? times ln function of oxidized species divided by reduced species. That is why I mentioned what the oxidized species are going to be and what the reduced species are going to be. So in our case, the oxidized species are Fe3+ and reduced species are Fe2+. So you're going to plug in the concentration of either. So ln of concentration of Fe3+ divided by concentration of Fe2+. So initially it was 1, right? Initially both were 1 mole per dm cube. So 1 divided by 1. So ln of 1 divided by 1, right? What would that be? That would have been ln of 1, which would have been e to the power 0. So it would have been 0. Therefore, R times T divided by Z, that is number of electrons exchanged, times Faraday's constant times 0. Therefore, the entirety of it would have been 0. Therefore, this proves that if your concentration of oxidized species and reduced species are 1 mole per dm cube both, in that case, your electrode potentials is E0. The one that is in standard conditions, right? So your electrode potentials will not vary until and unless you change your concentration, right? You change your concentration of ions of the oxidized or reduced species. Fair enough. So this is your formula. I have noted what each of those are. R is the gas constant given in the data booklet, 8.31, and T is the temperature, which is going to stay constant, 298 Kelvin. R is also a constant, and Z is the number of electrons transferred. So in case of Fe3+ being reduced plus electron turning into Fe2+, the exchange of electrons is 1. So in this case, Z is going to be 1. And F is Faraday's constant, which is also a constant, right? Times ln function of this. So the only variable over here is going to be the number of electrons transferred and what else? And the concentration, right? So the rest of the things you can multiply and divide and to get a more simplified equation, right? Now, in our case, since we have a bunch of constants over here, that is R, temperature, Faraday's constant, we can further simplify all of this into a more neat equation. How do we do that? So first of all, we know temperature is a constant. And this ln function, you can actually change it into a log base 10 function. How do you do that? So ln of x, is going to be, if I try to break this down, ln of x is actually log base e x. You don't need to know this, but you can directly use this formula, but I'm just showing it. So ln of x is going to be log base e, where is it? Log base e to the log base e of x, right? So now what can you do? You can do something simple. That is, you can bring log base 10 to this and to this. So log base 10 to x, log base 10 to e, right? So now you can write, so you have, where do I write it? So yeah, this you can simplify as, so if you calculate log 1 by log base 10 e times log base 10 x, right? So if you calculate, if you take your calculator out and calculate log base 10 e, log of e, that is, you're going to find the value to be 2.3026. So this value comes out to, where do I write this? So you can write this as 2.3026 times log base 10 of x times log base 10 of x. What is your x, by the way? Your x is this entire thing. This entire term is your x, okay? So this is how log base 10x is derived. I mean 2.3 times log base 10x is derived. So what are the things we're doing? We are substituting the constants with 8.31, that is R. We're substituting the temperature, 298. We're substituting the Faraday's constant, that is 96,500. And we're changing the ln function into log base 10 function. How we do that, you don't need to know. If you remember this much, you're good to go. And the other thing is your this part is not going to change. That is, you're going to directly plug in the value of concentration of oxidized species. So let's say initially it was 1 mole per dm cube, now it is 0.8. So you plug in 0.8. And if your reduced species concentration changes, you're going to plug in that concentration. So let's say from 1 mole per dm cube, it's now 0.9. So plug in 0.9 mole per dm cube. And then if you further simplify all of this, you're going to see your equation turns out to be E naught, electrode potential at standard conditions, plus 0.059. That is, after you multiply all of these constants, 0.059 is going to be your constant, divided by Z, that is transfer of electrons, because since it can vary, you have to keep this. So it can be change of 1 electron, 2 electron, or 3 electrons, right? Times log base 10 of oxidized species divided by reduced species. Fair enough. So this is your final equation in its final form. That is, why is it? Oh, so that is E naught, standard conditions, plus 0.059 divided by transfer of electrons times log base 10 of oxidized species divided by reduced species. So this is your electrode potential formula. That is, in case there is change in concentration of ions. Okay. Now, in case of Nernst equation, since we are talking about electrolysis, it's only going to deal with aqueous ions only. That is, the ions in the solution, right? So, fair enough. Now, if we want to understand how the calculation is actually done, let's look at it with an example. That is, if I take an half cell, that is a half cell of Mg and Mg plus 2 plus ion, that is going to be metal and metal ion half cell. So you have your beaker, you have your Mg electrode magnesium, and you have your Mg2 plus concentration, right? So what is your oxidized species over here? Remember to write your equation in the form of reduction taking place, and Mg2 plus 2 electrons forms Mg atom, right? So it is given to you that the concentration of both are the following. Mg2 plus concentration is 0.3 and concentration of Mg is 0.2. What are the oxidized species? Note, Mg2 plus is so oxidized species, ox, and Mg is going to be your reduced species, right? And under standard conditions, E naught is going to be minus 2.38 volt. That is 1 atmospheric pressure, 1 mole per dm cube of Mg2 plus, and pressure of 1 atm, did I say that? And temperature of 298 Kelvin. So under those conditions, your standard potential is minus 2.38. Now, under these conditions, such that your concentration has changed to 0.3 mole per dm cube and 0.2 mole per dm cube, respectively, what is the change to electrode potential? That is your half cell electrode potential. So your change to electrode potential is going to be your E naught, that is electrode potential under standard conditions, plus 0.059 divided by transfer of electrons, that is 2, times log base 10 of oxidized species concentration divided by reduced species concentration. So now if you simplify all of this, you're going to get minus 2.375 volt, right? The change is small but significant. So this is how you find out the change in electrode potential. Now I'll reconnect it to our theory that was over here, that we talked about how the equilibrium changes, right? Equilibrium shifts. So if we connect it to that theory, notice the concentration of Mg2 plus or the oxidized species is more. Therefore, if the concentration of Mg2 plus is more, that means more electrons will be used up to increase the concentration of Mg. Therefore, the concentration of electrons should decrease, right, to make more Mg atom. Therefore, our electrode potential is supposed to be more positive. Why? Because concentration of the negative charge, that is the electrons, decreases. So if that happens, your electrode potential should be more positive, which is exactly what has happened in our case. So our electrode potential increased, right? Became more positive, although it's still negative, but it increased, right? Became more positive comparatively. So therefore, our theory matches with our calculation. So this is it for this video. We understood the theory behind non-standard conditions, and we derived, we saw the formula for calculating electrode potential in non-standard condition. So that is going to be it for this video. We have one last video left, and after that, it's going to be done with electrochemistry. Fair enough. See you in the next video.